Hello everyone, so welcome to my YouTube channel again. So in this particular video, I will discuss about uh, the next rack pipeline code for PDF and question answering using Ollama and ChromaDB. So before going to this video, let's just discuss about what we have covered so far. So in the day one, you can see I actually covered the retrieval augmented generation, the rack pipeline. In this process, it includes two steps. First of all, data indexing, and the step two is that data retrieval and generation. Then I also covered how we actually load the data, split the data, and why we need to split the data, and the data embedding models, and also the data storage, how we will store our vector embeddings. And then the next thing, which is data retrieval and generation one. So in this way, user will ask the question. So we will use vector embedding for the user query, the same vector embedding that we have used right there for creating the vector embedding from the text chunks. So we will use the same vector embeddings model, whether you can use OpenAI vector embedding model, which is text embedding ADA 002, or you can use any open source model. So in this video, I will be talking about specifically how we can create a basic rack pipeline for PDF question and answering system using Ollama and ChromaDB. So let me first clarify those things. What is the purpose of this Ollama, and what is the purpose of this ChromaDB, and what is actually ChromaDB? So first, Ollama is a open source library. So if you didn't watch my previous videos, I have actually go through each of the steps how you can run and install Ollama in your local system. So you can check out my previous videos. So Ollama is a open source library. Via this, you can run any kind of large language models in your local system. Then the ChromaDB is a vector database. So it's a open source vector database you can use. So the basic rack pipeline, which will something look like this. We have a PDF file. So here, so this is my data, and we need to load the data from our hardware storage, and then we have to chunk the data. So we need data splitting for that, and for each of the chunk, we will create particular vector embeddings for each of the chunk. So for example, we have 10 different chunks of data, and we will create 10 different vector embeddings for each of the chunk. Then finally, we will store everything in our vector database. And whenever we will use the user query to fetch the result, you will look into this particular vector database. This is the same vector database that we will use right there for retrieval and generation process. So in this case, for vector database, for this one, we will use ChromaDB. So it's your choice. Basically, you can use any kind of vector database available. You can use Llama Index, you can use ChromaDB, you can use any paid services like Pinecone vector store, which will be more scalable. So it totally depends upon your applications, like in which domain do you want to work and how long or how large your data set is. And then for LLM, we will use Llama 3. So for generating the final response. So to run this LLM, which is Llama 3, we will need Ollama. So let's go to our code part, how we can actually implement this in our free Google Colab. So okay, so here is my code actually. So first of all, we need to actually do different things. So like as I said in the previous video, I have go through like how you can install Ollama in your free Google Colab. You can watch my previous videos. So first of all, let's just go to our code part. As I have discussed the earlier videos, I will add those videos in the description of this video. You can check this out. So this is the Ollama library, and for this we will use this particular Linux command to install Ollama in our Google Colab. So to go to our terminal prompt, we will install Colab Extram library and load ext Colab Extram. And then whenever we will hit this particular command, it will give us this particular command interface. So if I paste this command right there, you can see Ollama is already installed right there. And by default, Ollama is running on port 11434. And also you can also change the port as what port you want to run Ollama. Then I actually serve this particular API endpoint, which is called Ollama serve. So via this you can, Ollama serve, via this you can get this particular interface. So then you need to load any particular model. So as we didn't download any model, so if we run Ollama run Llama 3, it will first check whether this Llama 3 model is already there in our particular Colab notebook machine or not. Otherwise, it will first download this model from Ollama Hub, then we can also test. So you can see it successfully downloaded this Llama 3 model. And then for running Ollama, we can use a Llama index functionality. So Llama index also integrates Ollama. So pip install Llama index LLMs Ollama. And then there are other different libraries that I need to install for the next things. So Langchain Hugging Face, for then Langchain community and Langchain, pip install PyPDF for processing the PDF files, pip install ChromaDB, which is our vector store, and then from Langchain community document loader, PyPDF loader, as we have the PDF file. So let me discuss what is the PDF file. So this is our PDF file, which is attention is all you need. I think all of you guys know about this paper. So I just download this paper and upload into Google Colab. And for text splitter, which is recursive character text splitter from Langchain, and Langchain.vector stores, import chroma, Langchain.prompts, chat prompt template. So we can design our custom chat prompt template. Then Langchain underscore Hugging Face, import Hugging Face embeddings model. So as I showed you here, we need an embedding model. So here everything is actually open source model. The LLM that we are using, Llama 3, which is open source, the vector store, which is ChromaDB, which is also open source, and the vector embedding model, which is Allmini L6v2, which is again open source library. So basically then we have the document path. So I just click here and copy the path and paste right there. And the chroma path, basically the ChromaDB vector storage name. So you can give any name. So I just add rag underscore db. And then using the PyPDF loader, I load this particular PDF file, and then I split the pages based on different chunk size. So chunk size equals to 500 and chunk overlap equals to 50. So chunk size equals to 500 means for every 500 words, it will take this as a chunk. For example, this is our first chunk. And what is the purpose of this particular chunk overlap? So for example, I use chunk overlap equals to 3. So for example, this is my first chunk. And if we use chunk overlap equals to 3, that means from this is our first chunk. And when it will create next chunk, it will take from this, not from here. So from here to another chunk. So why chunk overlap needed? So basically it retains the relevancy of our documents. So like as we have our PDF files, so these are some sequential documents. So for example, after this sentence, then the next sentence came. So if we want to make the relevancy and also connect between our chunks, we can use chunk overlap. You can also set chunk overlap equals to 0. It's totally upon your it's totally depends upon your use case. And the best part is that you can try out different chunk size and chunk overlap. So whichever chunk size and chunk overlap works best for your application, you can use this. So it's not that hard logic that you need to use chunk size equals to 500. So generally people use chunk size equals to 1024 and chunk overlap equals to 0, or in some cases 50 or 20, something like this. Okay, so then we got our text splitter object. So then text splitter dot split documents, it will split our documents from these particular pages. So then we will get a list of chunks. So if we want to see our first chunk, how it actually look like, you can see it's a document object, and under this object there is a page content. So here this is our original text, and here you can see the metadata section. So the metadata section is basically necessary that in which page this particular chunks came. So it said that the source of this particular chunk is that this particular PDF, which is this one, and this is page 0. Basically in indexing we use 0 as a number 1 page. So basically it's from the first page. And if I want to see how many chunks right there, so you can see we have 93 total chunks. And then if I want to get the page content of our first chunk, so you can see this is our original text. And if I want to check any random 10th chunk, you can see this is our 10th chunk. And as I said, for embedding model, we will use Hugging Face embeddings, which is from sentence transformers all mini L6 V2. So you can use any kind of open source or closed source, any kind of embedding model right there. And so basically the embedding model that we will use right there. So we need to embed our chunk. So we have our ChromaDB, which is our vector store. From documents, we pass these particular chunks that we got, and we pass our embedding model. This is our embedding model, and persist directory equals to chroma path. So basically it will create a vector store called RagDB, and in this particular vector store it will store everything based on our chunks and convert our chunks into a vector embeddings. And then for retrieval and generation process, I have used llama index.llms.ollama, import Ollama, and this is our question. For example, user asked this question. So I just take a random question from this particular paper. You can go through this paper. It's a pretty, I can say, amazing paper. So the query is that how does the scaled dot product attention mechanism works, and what roles does the scaling factor play in its calculation? So this is our query, and we will pass this query using similarity search with score. we will pass query and k equals to 5. So if you are following my previous videos, I have discussed here. So for example, you have the query and you will create the vector embedding for your query, and then you will search into your vector store and it will give you a top k chunk. So this top k chunks is basically this one, which is k equals to 5. So out of your 93 chunk, it will give you top 5 chunk that are more relevant to this particular question that you have asked. This is the actual thing. And for extracting the more relevant information based on your query, it will use cosine similarity. So by default, ChromaDB use cosine similarity distant metric, but you can use any kind of distant metrics like dot product, or there are different matrices are right there. So basically we have our documents from our ChromaDB, which is called retrieved documents, which is these top k chunks. So which is these top k chunks, and those chunks we will pass to LLM. So in this case, our LLM is Llama 3. So you can see if I print these docs chroma, you can see there are 5 different chunks are right there. Why 5? Because we have put k equals to 5. If you use k equals to 3, it will return you top 3 results. That's how it actually works. And again, for each of the document, you can see there is additional parameter that also comes in, which is called 0.5071, 0.6167, 0.71024. So what is this actually means? This is mean the score, like how similar your documents are based on your particular query. So based on the cosine similarity metric, it will generate a score. And then we will concatenate everything, every top, the top k chunks into a list, and we will create a context text. And you can see our context text will look like this, something like this. And we will pass this context text to LLM. So here we'll pass this context text to LLM and the user query, then LLM will finally give us the response. That's how it actually works. So here we have created a prompt template, answer the question based only on the following context. So this is our context, which is here, and answer the question based on the above context. And this is our question. Provide a detailed answer. Don't justify your answer. Don't give information not mentioned in the context information. And do not say according to the context or mentioned in the context or similar. So basically you can also design this prompt template as your use case. You can also customize these things. So it's totally upon your application. And then we create a chat template, chat prompt template, and we pass our template, and we have our prompt, which is the context text and the query. And then finally we actually pass to our LLM, which is this one, this guy, this LLM. This LLM will finally give us the final response. So as we have downloaded our Llama 3 model, and we use request timeout equals to 60 seconds. And you can also add your base URL. So basically right now, as Ollama is running into this particular machine, we don't have to explicitly put base URL as a parameter. But for example, you are running Ollama in your different server. For example, GPU server in your run port server. So you can use your API endpoint as a base URL, and you can pass right there. So you can use this. It's pretty easy. And then we use model.complete, and we pass this particular prompt, and this prompt contains our context and our question. And based on our context and question, it will give us the final response. So you can see for this particular question, so what is our question? How does the scaled dot product attention mechanism work? And what roles does the scaling factor play in this calculation? And the response that LLM gives us that the scale dot product attention mechanism works by counting dot product of the query of each key and applying a softmax function to get the weights. The weight assigned to each value is computed as a scale dot product with the query, which corresponding to the key, and the scaling factor is this one. I think the response is pretty good, and as you know that Llama 3 is a very good model right now, open source in the open source universe. So you can try out different models, different data sets. You can try out any kind of data set, whether it is a Excel sheet, whether it is a PDF file, whether you can also scrape the data. So in the upcoming video, I will also discuss about different RAG architecture, how you can implement your RAG architecture efficiently. So till now, that's all from me. So if you have any query, please let me know in the comment sections. I will try to reply. So thank you.